I'm Spring Berman, and I am going to talk about a framework that my group is developing for control and estimation using robotic swarms. And specifically, I'll focus on the aspects of this that involve heterogeneity. So our overall goal is to design highly probable collective behaviors. So we are looking at systems where there is inherent stochasticity due to sensor and actuator noise. It could be program stochasticity, as in probabilistic search or target tracking. And so our goal here is to do the best we can and say we want some objective, such as retrieving a certain number of payloads within a certain amount of time, within a specified probability. And so the goal here is to have this high-level objective from a user, and then determine how many of each type of robot we need to complete the task. What are the set of tasks and task transitions, and what are the motion controllers, and to do all of this within a general framework. So this sort of echoes what Stefano was talking about earlier in terms of these objectives for robustness. Okay, so we think about this as deploying a swarm, which can be heterogeneous in terms of capabilities, into an unknown environment. And the swarm may not have access to GPS data, and it is restricted to local sensing and at most local inter-robot communication, so it may not even have communication. So the swarm in the course of exploring is going to have random encounters with robots and with features in the environment, limited computation, and we have been assuming that we have a broadcast control architecture, so the robots are either pre-programmed with these set of tasks and task transitions, or these are recomputed and broadcast by a supervisor. Okay, so I'm going to talk specifically about heterogeneity in terms of tasks and capabilities. So when I say tasks, I mean that the robot is performing some behavior that's associated with certain controllers, and it can switch between these tasks. So the same robot can perform multiple tasks, and at any given time, some set of robots are performing one task or another. I'll also talk at the end about heterogeneous capabilities, so robots with physically different capabilities. And so we consider that our swarm is deployed to the unknown environment, it disperses, and so we've been looking at several different classes of problems, and each one is associated with its own challenges, including how do we incorporate heterogeneity. So the first type of problem that we look at is mapping and covering boundaries. Okay, so clearly there's a spatial dependency there in robots crowding around the perimeter of some area that has to be accounted for. Okay. Also mapping and covering interiors. So perhaps the robots can cross over some region of interest or fly over, and you want a certain spatial distribution of coverage, or you just want to know what is the geometry of the feature. Again, they don't have localization, so you have to do this from unlocalized data. We may want to estimate some environmental scalar field reconstructed from the robot data. Another problem is to do cooperative manipulation of some payload that you don't know information about beforehand. And so another problem is that maybe you don't want your swarm to just diffuse out to low densities. Maybe you want to pose more structure via more capable agents that can herd or guide formation control of the swarm. Okay, and then finally, we have started to consider the fact that you may have limited observations of the swarm. So you may have just observations over a subdomain, and you have to understand the swarm's collective behaviors and understand the environment just based on these localized observations. Okay, so this kind of illustrates that maybe you need to construct a scalar field as well. So we've been approaching this with a control framework that's based on multiple levels of abstraction. of the swarm. So we consider at the individual level what we call a microscopic model. And so this models actions of individual robots, as in this simulation. But there are challenges associated with using this for control. So what we do is abstract this, and so we've been using the model of chemical reactions, chemical reaction networks, which Amanda talked about yesterday. So these model interactions between robots and their task switching based on either spontaneous decisions or encounters with things in their environment. So based on that, we can use abstractions, these mean field models, which have been used in chemistry and population dynamics and biology. So these consist of differential equations, and now we've reduced the dimensionality of our state space to just looking at trajectories of populations of robots in different tasks over time. And so now this is independent of the swarm size, and also we can use these nice techniques from analysis, control, and optimization to guide the collective behaviors in this lower dimensional space with theoretical guarantees on performance. Okay, so the simulation I showed you was a well-mixed swarm in that the spatial density was fairly homogeneous over time, but of course that's not always going to happen in practice. So we can include spatial dependency using partial differential equation models that govern the dynamics of now these density fields of robots and other features over time. Okay, so the types of PDEs that we're using are called advection, diffusion, reaction PDEs. So here, advection is modeling this deterministic velocity field that you can program the robots with, and diffusion is modeling the random behavior. So the randomness that's either programmed or it's just inherent in the motion of the robots. And so what we can do is abstract our microscopic model to our set of PDEs, and now we can design the velocity field, the diffusion coefficient of the swarm, the degree of random motion, and the rates at which they switch between tasks, as shown over here, modeled as a chemical reaction. So here, this is showing you the effect of designing a spatially dependent rate constant, so that the robot switch from task A is moving, task B is stopping, so that you get a certain pattern of the swarm over the area. You can basically do the same thing by designing the velocity field to have these periodic sinks. You get a similar pattern. So you can design these parameters for these different patterns of collective behavior. And so we've applied this in the specific application of commercial pollination. This is a picture of, well, early picture of a RoboBee from the RoboBees project at Harvard. So we're assuming that if we have a swarm of RoboBees, you send them out over a field, you want them to pollinate the field according to a certain spatial distribution of pollination activity. So maybe some of these crop rows need more pollination than others, for instance. So you can achieve this using just two simple behaviors, or two sets of task transitions. So the robot can go from flying to a time-dependent hovering rate once it locally senses it's over a certain type of flower, and we're assuming that it can do that. And then it can go from hovering to flying again at some probability rate. And so our goal here in this problem is to design the velocity field that we're deploying the swarm with, and their hovering rate, the rate at which they start hovering. So we can formulate our macroscopic PDE model. We have an environment which might have obstacles, and we're going to encode the regions, the crop rows, as the spatial indicator function. So here in this application, we're assuming we know those indicator functions, we know the geometry of the domain. We can formulate an optimization problem where we're trying to minimize the difference between the target spatial distribution and the actual spatial distribution at some time. So we're fixing the end time. And our constraints now consist of the PDE model, the macroscopic model. And so we've done this, optimizing the velocity field and hovering rate for different objectives. So in this case, we want the swarm to achieve this kind of striped spatial distribution. So it automatically optimizes the control parameters for that. We can also reduce the deployment time allotted. Say we want just the right 2 rows to be pollinated, and so the optimization problem gives you the control inputs that will do that. So it's a kind of a flexible framework for different objectives. So we've also extended that approach to mapping, so we don't know where the crop rows are beforehand. So we can use similar optimization problems to actually back out what those spatial indicator functions are, and that corresponds to the map of the environment. And so we can do that for both coverage of interior regions, as you see here, using only temporal data from the robots. Again, not localized. We can also do this for mapping geometries of boundaries of features. Okay. All right, so then moving on to the problem of boundary coverage. Now we have spatial issues with robots surrounding a certain boundary. A robot may come in and not be able to fit on the boundary, so we have to account for that, that fact. And so this looks similar to, so in material science and chemistry, this phenomena of adhesion. Adsorption. So smaller particles attaching to the surface of a larger particle. And so what you can do here is design your set of tasks and task transitions in such a way that it minimizes the challenge involved in these spatial effects. And so specifically here, a robot sees a free site on the boundary and it attaches with some probability, or it detects a local robot that's free and it detaches with some probability. And so we can abstract this to a macroscopic model. And so the benefit of this is that the equilibrium allocation around boundaries, which we can control, is only dependent on the ratio of encounter rates with bound and unbound zones. And so this ratio is easier to characterize than actually trying to find the absolute encounter rates. And it's also robust to the type of environment. So we can look at a variety of scenarios with different numbers of these boundaries, different numbers of robots, different sizes, and we get the same relationship between what we expect the allocation to be and the actual allocation, which is affected by these spatial factors. So that's pretty useful. And so we've also kind of leading into the next application, which is collective transport, which does involve boundary coverage. But the additional challenge here is including the dynamics of the payload. So we've addressed this using a hybrid systems framework. So now we've added dynamics, so the discrete task switching plus the dynamics of the payload. And we've also drawn inspiration from biology, so specifically ants. So certain species of ants are very good at collective transport. And this is a video of desert ants that live in Phoenix. And this is taken by Professor Stephen Pratt at Arizona State. So he collaborated with us so he provided data on these ants moving this artificial load. And so we developed this stochastic hybrid system model to describe the set of tasks that the ants switch between, as well as a simple model of the dynamics of the load. Okay, and so we fit our model to the averaged data over 17 trials of these ants, so that we got a model that predicted the population dynamics of ants in different tasks or states, so ants on the front, back, and detached, as well as the load dynamics. And then we combine this with our work on boundary coverage that's robust to the environment to get these ant mimicking set of transitions and tasks. And so our simulated robots, or ants, were able to mimic the population dynamics of the actual ants. And so I'll talk a little bit more. Now here, all the ants we're assuming are homogeneous, that they have the same set of tasks and capabilities. I'll talk a little bit more about heterogeneity later on. So I just want to move on to the topic of heterogeneous capabilities. So if you have, so not only can the robots switch between heterogeneous tasks, but maybe some of them are more capable than others. Maybe some of them do have access to GPS. So what you can do is control, for instance, the swarm structure, excuse me, using these kinds of leader-follower schemes. On the left is formation control, using boundary control of the wave equation. On the right is this confinement control, using averaging theory. And so you can actually incorporate these inter-robot interactions into the advection field of the PDE model, potentially. This is some of our future work, in order to increase the cohesiveness of the swarm. Okay, and so we have been developing hardware for heterogeneous capabilities. So this is our small robot Pheno, we call it Pheno. And so it has a base module here, but you can also design your own attachments, such as this 3 degree of freedom gripper arm. And so you can make a heterogeneous swarm, as shown here. And so we've done some experiments with cooperative manipulation, and so we intended to use them more for experimental validation. And so just a last note on, so I did mention at the beginning using just local observations. We can do things like scalar field estimation using, perhaps there's a few capable agents that have access to some observations. They see the swarm diffusing. The swarm itself can measure properties of the environment or take measurements of the scalar field. So they're just running a diffusion equation basically. And then after some time, based on the observability of the heat equation, these observers can back out what the scalar field looks like. Okay, so this work will be presented at CDC. Okay, and so finally, so I said I mentioned heterogeneity in collective transport. So now we have been assuming all the ants are the same, but they're not, obviously, so some ants are stronger than others. Stephen Pratt and his former postdoc Early took some more recent data, or videos of ants that were just pulling this, what we call a chariot of some straws kind of stuck together. And so they're pulling on threads, and they're trying to get it back to their nest. So we're trying to figure out how do the ants do this, so from a statistical analysis, it looks like the ants are moving, the team is moving at the speed of the slowest ant. So we're trying to devise control policies that will mimic this, and so we're trying to take a neural network approach right now because it's hard to prove stability about controllers of heterogeneous vehicles. So this is ongoing work that we're looking into. And then finally, we're going to so going back to my first slide, what we really want is to be able to have these high-level specifications, and then you generate this heterogeneous swarm, heterogeneous in terms of the physical capabilities and the set of tests that they perform. And so we're trying to develop a principled way to do this for different applications. For instance, we have collaborative work with Andrea Bertozzi at UCLA on using numerical analysis techniques from fluid dynamics to quantify the difference between the macroscopic, microscopic PDE models, or macroscopic PDE and microscopic model, and then achieve achieve a target objective like coverage within a certain accuracy. And we've also done some work on, this is submitted work, that looks at figuring out the number of robots and their sensor or communication range that will result in expected statistics of connectivity around a boundary, for instance. And so at the beginning I mentioned we're assuming a broadcast controlled architecture, but we would like to move towards decentralized policies for estimation and control. And so that will allow the swarm to adapt to different objectives that the swarm perceives in a decentralized way. So I'd like to thank my students who contributed to this work,